Hello, this video covers Physics 2211 Lab 2. In this lab, we were tasked with recording an object's position and time as it fell, starting from rest. Since we know the object's final and initial position over various time intervals, we can calculate its velocity over those intervals. If not, we can also calculate velocity by dividing F net by mass, which gives acceleration, and multiplying that by the time interval. And then using this velocity, we can find the object's final position at the end of the interval. In my equation, I use V average, but you should use VF when the force isn't constant. I made two computer models using these equations to predict the ball's future position and velocity. One of them models neglects drag, and one of them takes drag into consideration. If we consider drag, then we must also calculate Fd, the drag force, which is b, some constant, multiplied by the square of the speed times j hat, because drag always points upwards, opposing gravity. And then F net is then Fd plus Fg. These calculations are very useful to us because we can use them to predict the future positions of objects. We can make many iterations with small delta t, and the smaller the delta t is, the more accurate our predictions will be. We can also calculate an object's terminal velocity, which is when the drag force equals the force of gravity. In other words, F net equals 0. Here's a video of me dropping a paper towel ball. I imported this video into Tracker and plotted the position versus time of the ball. Now this graph is very useful for us because not only can we see how its y position changes with respect to time, but we can also see how the velocity changes because the slope of this graph is the velocity. And as you can see, the speed increases over time, because the object is accelerating downwards due to gravity. So at the very beginning, the velocity slope is relatively flat, almost 0, but as time increases, the velocity of the object also increases and the slope gets steeper. If I drop the ball from a higher elevation, then the object will eventually reach terminal velocity, which is when acceleration is 0, and therefore the slope of the graph would be a constant. I modeled what the position of the ball would look like if there was no drag. As you can see, there's a similarly arc-shaped position versus time graph. However, the final y position is lower than it is in reality. The ball falls more further down the y-axis. Also, the velocity versus time graph is a straight line, unlike as you saw in the tracker graph. Since there is no drag, acceleration is constant, and because there is no drag, there's also no terminal velocity, which means that the object will continue accelerating forever. I also made a model with drag. As you can see, the position versus time graph is very similar to the one in Tracker. However, the velocity versus time graph is curved. Because there is a force upwards, the velocity isn't constant and it gets less, and the acceleration gets less and less over time. And after enough time, the acceleration will be 0 because of drag force. This is when the object reaches terminal velocity, and the velocity versus time graph will have a slope of 0 and become horizontally flat. I plotted all three position versus time graphs on this plot with the actual position measured in Tracker with the blue line, the predicted position without drag being the orange line, and the predicted position with drag being the gray line. And as you can see, the predicted position without drag is lower than the actual. This is because there is no upwards force, and therefore the object is able to fall farther. There is also, as you can see, the blue and gray lines are almost identical to the actual position. I had to do some trial and error to figure out the approximate B value, and I estimated it to be 0.272. But however, you can see there's still some deviation between those two lines. That raises the question, how can we fix that? So to improve my data, I think I can be a little more careful with placing the point at exactly the center of the ball and tracker. In some frames, the sun made it hard to see where the ball was, and in other frames, especially towards the end, the ball was a bit blurry. I should probably also use an object with a more consistent B value. Since a paper towel ball is not symmetrical, as it falls and rolls, different parts of the ball are sticking out at different angles, and so therefore the forces acting upon it may not always be balanced, and I should probably use an object that is more symmetrical around. What if I threw the ball downwards? I made a model for that as well. As you can see, both of the graphs, both the position versus time and the velocity versus time graphs are very similar. However, the object will travel further down the y-axis. Since it's moving at a faster speed, it will cover more distance in the same amount of time. The velocity versus time graph also starts at a different value. At t equals 0, velocity is -1 meters per second as opposed to 0 meters per second because I would be throwing the ball down at that velocity. However, all of the graphs, this one and my other predictions that incorporate drag, will have the same terminal velocity. Since Fg is the same everywhere on Earth, it is the velocity at which Fd equals Fg would also be the same. However, in this case, the ball would reach terminal velocity sooner since it has a greater initial downward speed. Thank you.